Let's look at another optimization problem. This is to do with optimal ranching pens. A rancher with 750 feet of fencing needs to keep her cattle separated into 4 groups. To do this, she wants to enclose a rectangular area and then divide it into 4 pens with fencing parallel to one side of the rectangle. The question asks us, what is the largest possible area of the 4 pens? And remember, the way we think about these optimization problems is you draw names for max, min. And I just put max up here because we're trying to maximize the total area. And so for U is for understanding, and the key thing to understand is what's known and unknown. And so here, what's known is 750 feet of fence. And what's unknown is the dimensions of the rectangle. So let's draw the rectangle out here. Okay, we'll call this dimension X and this dimension Y. And we want to have these pens in here. And we need 4 pens, so we need 3 additional dividers. And so we're going to call X as the length of the rectangle. And then Y is the width of the rectangle. And then the thing we're interested in here is A, the area of the rectangle. Okay, so we have this constraint that we only have 750 feet of fencing. And so we can turn the constraint into a formula. So we have 750 is equal to the entire length of fencing, and that's going to be 2 times y plus 5 times x. So that's our first formula. Our second formula is a formula for the thing we're trying to maximize. So it's the area, and the area, because it's a rectangle, will simply be x times y. Our next step is to use the constraint and to rewrite one variable in terms of the other. So we could either use the constraint to write y as a function of x or x as a function of y. It doesn't matter which one we do, we'll come up with the same final answer for the problem. So in this case, I'm going to solve for x as a function of y. And so we have 5x is equal to 750 minus 2y. Therefore, dividing by 5, we have x is 750 over 5 minus 2/5 y. And this is equal to 150 minus 2/5 y. So now, when we write the formula for the area, we can write A is equal to x times y. But we have our formula for x here in terms of y, and we'll plug that in. And so, using the constraint, we're able to write x as a function of y, and therefore A is only a function of y. And we can expand this out if we want to as 150y minus 2/5 y squared. Now we're interested in maximizing A, and so we want to find a critical number, i.e. a value of A such that A prime is equal to 0. The other criteria for a critical number would be where the derivative does not exist, but that's not relevant here because A is a polynomial, so it's differentiable. And so let's say 0 is equal to A prime of y is equal to 150 minus 4/5 y. we can solve this for y, and it gives 4/5 y is equal to 150, and multiplying both sides by 5/4 gives us y is 5/4 times 150, which is 187.5. So we have the value of the critical number, which is right here, and we want to make sure that the critical number is giving us a maximum, not a minimum. And the easiest thing to do here is to use the second derivative test. So if we write a double prime of y, we have minus 4/5, which is less than 0. And so that says the function a is like a sad face, and so when we find a critical point, it's going to be a maximum. Our alternative here would have been to use the first derivative test. We could have used that, it just wouldn't be quite as easy. So when you get to this point, you just take a look at the two tests and decide which one is going to be the most convenient to use. So we do have 187 gives a max, which is what we're looking for. And what is that maximum value? It's a of 187.5. And we have the formula right here for a. It's 150 times 187.5 minus 2/5 times 187.5 squared. And if we put that on the calculator, that's 14,062.5 square feet. And so that's the answer. And so the rancher can use this to work out the dimensions of the pen and then to optimize the area relative to the amount of fencing that's available.